Today we are talking about section 7.4, which is talking about special right triangles. But before we go into that, I want to go through the warm-up that was done for this section to give us an idea of how these work. So if this is a square, we're going to solve for x if this square brick has side length 2, a separate situation if it has a side length of 3, and a third situation if it has a side length of 5. And we're going to write our answers in simplest radical form. So starting with side length being 2, we'll solve for x if the side length is 3, or if the side length is 5. So if this is a square and the sides are 2, since this is a square, we also know this is a right angle, so here we have a right triangle. To solve for x, using our Pythagorean theorem, 2 squared plus 2 squared equals x squared. So 8 equals x squared. 8 is the square root of x. And simplifying the square root of x, that is 2 root 2. For a separate situation, let's say we still have a square. We're still solving for x, but our sides are 3 instead. Well, again, this will be 3 squared plus 3 squared equals x squared. So 18 equals x squared, and the square root of 18 is x. So this ends up being 3 square root of 2 equals x. Now you might be seeing a pattern forming here that when the side lengths were 2, x was 2 square root 2. When the side length was 3, x was 3 root 3. So if this is 5, you might predict this would be 5 root 2. So 2 root 2, 3 root 2, and 5 root 2. So 5 squared plus 5 squared should equal x squared in this right triangle here. So the square root of 50 is x. So this does end up simplifying to 5 root 2. This is a property of a special type of triangle called the 45-45-90 triangle. If this is a square, we know the diagonals in a square bisect each other, so these are 45s, and these are 45s. So this is a 45-45-90 triangle. In a 45-45-90 triangle, the hypotenuse always equals the leg times the square root of 2. So when it was 2, this was 2 root 2. When this was 3, this was 3 root 2. When this was 5, this was 5 root 2. When it's x root 2, no matter what x is. So this is theorem 7.8 talking about 45-45-90 triangles. These come to be very useful and very important when you get to certain aspects of trigonometry. Excuse me. So you can pause it if you still need to write this, otherwise we're going to move forward now. Find the length of the hypotenuse. Well, for part A, this is a 45-45-90 triangle because if all 3 of these should add to 180, this has to be 45. Let me pause there. Sorry about that. And if those are both 45, this is isosceles. This is also 8. And in a 45-45-90, the hypotenuse equals the leg times the square root of 2. So the hypotenuse is simply going to be 8 root 2. That's simple. For part B, we know this is a 45-45-90 because this is isosceles. So these have to be equal. And since they all need to add to 180, these both have to be 45. There's no other choice. Isosceles, right triangles are always 45-45-90s. There's no other option. So the hypotenuse equals the leg times the square root of 2. Well, here the leg is 3 root 2. I want to take that times the square root of 2. And root 2 times root 2 is just 2. So the hypotenuse is 6. Excuse me. Let's try a third example. Let's say now we're going to find the legs, and we know the hypotenuse. Well, again, this is isosceles and a right triangle, so these have to be 45 degrees. And we know the hypotenuse equals the leg times the square root of 2. Well, here our hypotenuse is 5 root 2, and we don't know our leg, but 5 root 2 equals L root 2. L has to be 5. And you can use mental math to simply say that x is 5. This is 5 root 2. 5 is your leg. Or if you like to do it the longer algebraic way, just to get a grasp of the concept, We can divide both sides by root 2 here, and the leg is 5 still. So it's easy. If this is 5 root 2, the leg is 5. If this was 12 root 2, the leg would be 12. If this was 16 root 2, the leg would be 16. But the question is, what if this isn't something root 2? What if this is just something like, I don't know, 12? Let's try that. So the hypotenuse equals the leg times the square root of 2. Our hypotenuse is 12. We can divide both sides by root 2. So these cancel, and your leg is 12 over the square root of 2. However, this is not simplified, so we'll still need to simplify this. No, we can't break down the root 2 into any other factors. However, we can't leave a square root in our denominator. You should never have a radical in your denominator. We will have to do what's called rationalizing to get rid of this radical or this irrational number in your denominator. So to do that, we know if we multiply 12 root 2 over root 2 times 1, we still end with the same thing. So instead of writing 1, I'm going to write root 2 over root 2, which is equivalent to 1, because anything divided by itself gives you a quotient of 1. The reason why I chose root 2 over root 2 is because that's my denominator, so when I multiply across, I have 12 root 2 over regular 2, because root 2 times root 2 is 2. And then I can divide 12 and 2 to get 6, so my answer is 6 root 2. If you want any additional assistance with rationalizing, feel free to look at videos on Khan Academy for that. If you want to do that now, or come see me before or after school, or email me, and I'll be happy to give you some assistance with that. If you like pattern, you can usually take your hypotenuse and divide it by 2 and add a square root to it, as some of you mentioned to me in class. But let's move on from 45, 45, 90s, and let's look at a second type, which is called a 30, 60, 90, which the angles are 30, 60, and 90 degrees. And there's two special properties of 30, 60, 90s. The first is that your hypotenuse equals 2 times the shorter leg. Because again, we have a short leg and a long leg this time, since they're different legs. The long leg equals the short leg times the square root of 3. And those are our two special properties with this theorem. Notice that the short leg is common to both of these properties, so if you know what the short leg is, it's a very quick problem. So let's say the short leg is 7. Well, this would be 7 root 3, and this would be 2 times 7, or 14. And we're finished. It's a very quick problem if you know where the short leg is. Let's say the short leg wasn't 7, let's say it was 9. So this would be 9 root 3, and this would be 9 times 2, or 18. You can pause this if you're still writing, otherwise I'm going to move on to do 2 examples. So, moving on now. We're going to find the values of x and y, writing our answer in simplest radical form. Well, let's start with solving for x. X is our short leg, so we want to find that. And we know our long leg. So we can say our long leg equals the short leg times the square root of 3. And we'll plug in what we know. The long leg is 9, the short leg is x, and then root 3. And then divide both sides by the square root of 3. So x equals 9 over root 3. However, we will have to simplify this since we can't leave a radical in our denominator. So we'll multiply times root 3 over root 3. So when we multiply across, 9 times root 3 is 9 root 3. 3 times root 3 is whole number 3. And then divide 9 by 3, and this is just 3 root 3. And that's x. Find your hypotenuse, and I'm going to erase all this stuff over here now. Our hypotenuse is whatever the short leg is, times 2. So our short leg is 3 root 3, and then just multiply that times 2. So we multiply our two whole numbers, and this is now 6 root 3. And we're finished. Let's do one other example before we finish this video. So we'll do number 5, find the value of the variable. Well, we know the short leg, we want to find the long leg, We know that the long leg is the short leg times the square root of 3. So x equals root 3 here times root 3. And root 3 times itself is just whole number 3. So that's what x is. So as you can see, we can find the missing side knowing only one other value, where for the Pythagorean theorem, we need to know 2 of the values to find the third one. So if you just know one value, you can't use the Pythagorean theorem anymore. You can use properties of a 30, 60, 90. Well, what happens if it's not 30 and 60 and 90? What if it's 50 and 40 and 90? Or something of that nature? Well, that's when trigonometry comes into play, which is the next video. If you have any questions, feel free to email me or see me before or after school.